Hey everyone, and welcome to this explainer. Today, we're going to demystify the literal magic of our modern world and turn some of your most mundane daily routines into, well, a series of awe-inspiring scientific encounters. I mean, think about it. We are completely surrounded by these absolute miracles of engineering, physics, and computer science that we just totally take for granted. Seriously, from the second you wake up to the minute you close your eyes, you're interacting with phenomenal tech. So my goal today is to pull back the curtain on these everyday items and show you exactly how they work. Right, so really think about this for a second. You push a button, and suddenly your food is hot. You tap a flat piece of glass, and a message instantly shoots across the entire globe. It's wild. So let's dive into this and look at the underlying physics, engineering, and computer science that make our daily technology possible. I promise you, by the end of this explainer, you are going to look at your house, your car, and your daily commute in a completely different, much more fascinating light. So here is our roadmap for today's explainer. First, we'll cover the invisible waves around us. Second, we're decoding the daily patterns. And third, we'll get into the physics of physical interactions. Let's jump right in. All right, section 1, invisible waves around us. We're going to take a look at the sea of frequencies we're constantly swimming in, specifically focusing on microwaves, Bluetooth, and GPS. Okay, first up, how on earth does a microwave heat food without any fire? It's a question you've probably wondered about when you're just standing there heating up yesterday's leftovers. For thousands of years, right, humans relied entirely on thermal conduction from a fire to heat food from the outside in. But your microwave, it does something completely different. There's no fire at all. So how exactly does the center of your bowl of soup get piping hot while the air inside that box stays completely cool? Well, the core concept here is something called dielectric heating. Now that sounds super complex, I know, but it really just means your food gets hot because we are literally making the water molecules dance. Unlike a regular oven that just heats up the air around the food, a microwave directly targets the internal makeup of the food itself, specifically its water content. So the crucial point here is this highly efficient 4-step process. Inside your microwave is this little device called a magnetron. This magnetron creates high-frequency waves, and those waves bounce all around the metal interior of the box so they don't escape. When those waves hit your food, they actually cause the positive and negative ends of the water molecules to rapidly flip back and forth. We're talking millions of times a second. They completely agitate the water molecules, and all that molecular friction creates the heat that cooks your meal. So it's friction, not fire. Moving on to another invisible wave, we've got to ask how Bluetooth flawlessly streams high-fidelity music from your pocket straight to your ears without a single physical wire. I mean, we use it in our cars, our portable speakers, our smartwatches, but how does it actually maintain that stable connection? Well, the answer lies in short wavelength UHF, or ultra-high-frequency radio waves. Now, unlike those massive radio waves that broadcast FM radio across an entire city, Bluetooth uses very specific short-range waves. These create a secure personal area network, sometimes called a piconet, just for your specific devices. And this is where it gets really cool. Inside your phone and your headphones are these tiny computer chips. These chips talk to each other by rapidly hopping across 79 different channels within the 2.4 gigahertz frequency band. And they switch channels thousands of times a second. This frequency hopping is absolutely crucial because it ensures that your music doesn't get interrupted by someone else's devices. It avoids interference and keeps your data perfectly synced up. All right, our final invisible waves technology brings us to GPS. Think about the absolute miracle of modern mapping software for a second. How does a little plastic and metal rectangle in the palm of your hand know your exact coordinates on a massive planet, down to just a few feet, even when you don't have a cellular signal? It all relies on a mathematical principle called trilateration. Now, people often confuse this with triangulation, which uses angles. But trilateration determines your position strictly by measuring absolute distances from known points. And in this case, those points are satellites orbiting the Earth roughly 12,000 miles above our heads. Here is how that math translates into your exact location. The GPS satellites are continuously broadcasting signals that contain their location and the exact time the signal was sent. The receiver in your phone logs the precise arrival time of that signal. By calculating the tiny delay between when it was sent and when it was received, your phone calculates its exact distance from the satellite. Once it does this with at least 4 satellites, it basically uses those intersecting spheres of distance to mathematically pinpoint your exact spot on the globe. It's just incredible. All right, moving right along to section 2, decoding the daily patterns. We're transitioning from invisible waves to the unique visual language of barcodes and QR codes. So every time you check out at the grocery store, you hear that familiar beep. But you might wonder how those simple, varying black stripes translate instantly into a specific product name, an inventory update, and the exact price in the store's computer system. Well, a barcode is simply an optical, machine-readable representation of data. But okay, get ready for a mind-blowing fact for your next trivia night. The laser scanner, it isn't actually reading the black lines. Nope, the laser reads the light reflecting off the white spaces between the black lines. The scanner detects those varying widths of white space to decode the numbers, which the computer then looks up in its massive database. But lately, QR codes are literally everywhere, right? On restaurant tables, concert tickets, billboards. So why exactly did we transition from those classic barcode stripes to these highly pixelated, static-looking squares for so many of our daily tasks? That massive leap in technology really comes down to dimensions. See, while traditional barcodes are one-dimensional, meaning they're only read horizontally from left to right, they can only hold a very limited amount of numeric data. Usually it's just a product ID. But QR codes, which stands for Quick Response, are two-dimensional. Because scanners read that grid of squares both vertically and horizontally, they can store a massive amount of data. A QR code doesn't just hold an ID number. It can hold an entire website URL, contact information, or even a whole text document, all within that single little square. Okay, finally, Section 3, Physics of Physical Interactions. Let's explore the mechanical and electrical ingenuity behind two things you likely physically touch every single day: touchscreens and elevators. Honestly, this one feels like pure magic. You're dragging a finger across a completely flat, solid piece of smooth glass, yet your smartphone flawlessly tracks your intricate finger movements, pinch zooms, and rapid typing, and there are zero moving parts. So how does the glass actually know what you're doing? The secret here isn't pressure at all, it's electricity. It relies on a property called capacitance. Now, capacitance is simply the ability of a system to store an electrical charge. And the magic ingredient in this system? It's you. Because the human body is mostly water and dissolved minerals, you are an absolutely excellent conductor of electricity. So here's what happens in literally a millisecond. Your phone's screen maintains this continuous, invisible electrical grid just beneath the glass. When your finger touches the glass, your conductive body literally absorbs a tiny, imperceptible bit of that electrical charge. This creates a tiny voltage drop at that specific contact point. Your phone's processor instantly calculates the exact X and Y coordinates of where that charge dropped, and it translates that into a tap, a swipe, or a keystroke on your screen. Finally, let's look at a mechanical marvel: the elevator. When you step into a metal box with a dozen strangers, how does this system effortlessly hoist thousands of pounds directly up, fighting against the force of gravity hundreds of times a day with incredible safety and smoothness? Okay, let's dive into this final mechanism because it's brilliantly efficient. An electric motor turns a sheave, which is essentially a heavily grooved pulley, while steel ropes lift the elevator car. But the true genius of the elevator design is a massive counterweight attached to the other end of those ropes. That counterweight weighs exactly the same as the empty elevator car, plus about half its maximum passenger capacity. Because this weight perfectly balances the load, the electric motor doesn't actually have to lift the full weight of the car. It only has to overcome the friction and lift the difference in weight. Gravity is literally assisting the system whether you're going up or down. That means the motor only expends a tiny fraction of the energy you'd expect for such a heavy lift. So as we wrap up this explainer, I really hope you can start to see the incredible science that's hiding in plain sight all around us. From the microscopic hops of Bluetooth frequencies to the massive counterweights moving our skyscrapers, the ordinary is actually quite extraordinary. Which leaves you with one final thought. The next time you use a perfectly mundane tool, what piece of everyday magic are you going to investigate next? Stay curious, everyone, and keep learning.